A-Level Paper 2, June 2019. This equation is about amines. Remember, amines have N's in them. So an NH2 is a primary amine because the N is bonded to one carbon. An NH is a secondary amine where the N is bonded to two carbons. And if there's just an N bonded to three carbons with no H's, it's a tertiary amine. Give an equation for the preparation of 1,6-diaminohexane by the reaction of 1,6-dibromohexane with an excess of ammonia. Well, first of all, you've got to know what 1,6-dibromohexane is. So it's 6 carbons with H's and a Br, one at carbon number 1 and one at carbon number 6. So there's a Br at either end of a 6-carbon chain. It reacts with 2 ammonias, so we need excess, plenty of ammonia. That's the condition for a reaction of ammonia. And the NH3 replaces the Brs by nucleophilic substitution. The Br comes off as Br minus, the NH3 breaks an H off and it forms 2 moles of HBr. HBr incidentally reacts with 2 more ammonias and makes ammonium bromide, NH4Br. If you take everything from the left and everything from the right, the 2 HBr's cancel and you end up with this equation here. Br CH2 6Br, so 1,6-dibromohexane with 4 moles then of NH3 because 2 extra moles of NH3 have reacted to make the ammonium bromide. NH2s at either end where the NH3s have replaced the Brs and H is broken off to make NH2 amine groups at number 1 and number 6, 1,6-diaminohexane that is, and 2 moles of ammonium bromide, NH4Br. Complete the mechanism for the reaction of ammonia with 6-bromohexyl amine, so this must be this chemical here, to form 1,6-diaminohexane. So there's an NH2 at one end and this NH3 is going to replace this Br. There's a carbon at each of these points here, so there's a carbon 1, 2, 3, 4, 5, 6. So there's a carbon there at that point. And that NH3 is going to use its lone pair of electrons. Remember, arrows can only ever travel from lone pairs or double bonds, single bonds or rings, so it's got to come from a lone pair of electrons on the NH3 and it's going to bond to, react to the carbon and the Br is going to break off. So it does this, so the NH3 bonds to the carbon and then the Br comes off and it's actually going to make this NH3 with a plus on the end. So the NH3 has replaced the Br on that carbon there. So the carbon's still there and the NH3 has replaced the Br where the Br was. There's a plus on the N and the H breaks off to leave NH2 and the plus then it disappears because electrons have been moved onto the plus and it makes H plus, NH2, NH2 at either end, and there's your mechanism. Suggest a structure of a cyclic secondary amine that can be formed as a byproduct of this reaction. Well, what actually happens is instead of the NH3, the NH2 at this end here, which has a lone pair of electrons, bonds to the C instead. So instead of an NH3 bonding and having nucleophilic substitution with on this carbon here and the Br breaking off, the actual NH2 on the other end actually bonds. Have a look how many carbons there are. 1, 2, 3, 4, 5, 6. So that's 6th carbon there, the N bonds to. So it's going to make this 1, 2, 3, 4, 5, 6 carbons, and that N on this end has bonded to this C here. So it's bonded to a C and there's still 6 C's in there. NH2 here has a plus on the N because the N has given away electrons, become a plus, and H breaks off, removes the N plus and leaves NH, and that's your cyclic compound. 1,6-diaminohexane can also be formed by a two-stage synthesis starting from 1,4-dibromobutane. So dibromobutane, Br, 1 at 1 and 1 at 4, carbon number 1, 2, 3, 4, And because, if you notice, butane becomes hexane, it gets 2 extra carbons. So CNs are used. Cyanide ions can lengthen the chain from bute to hex, and I'm going to need 2 of them to replace the 2 Brs, and therefore it forms this compound here. 1 carbon, 2, 3, 4, 5, 6. It's going to form nitriles. And so it will, I'm going to need cyanide ions. I use cyanide, potassium cyanide makes cyanide ions, and I use methanol and water and methanol to create these cyanide ions. So the potassium cyanide dissolves in water and methanol. The potassium part is a spectator ion. It's the Cn minus and the lone pair of electrons that are involved in the mechanism. Now then, I want to turn this into 1,6-diaminohexane, so I've got to turn these N's into NH2s. To add H2s, the easiest way to do that is hydrogen and nickel. So the reagent is hydrogen and nickel is a catalyst. That's the condition. Explain why 3-aminopentane is a stronger base than ammonia. Well, when something with an N in it, an amine, reacts as a base, it reacts with an H+. Bases accept H+, and it uses the lone pair of electrons to bond to the H+. And what actually happens in 3-aminopentane, which is this chemical here, the N has a lone pair which is available. It's more available than in ammonia because of something called a positive inductive effect. That's where this carbon chain repels electrons away from itself. Just like a methyl group, this chain will repel electrons away from it and increase the availability of the lone pair of electrons, so that this NH2 group, this amine group, can then act as a base and accept H+. Justify the statement that there are no chiral carbons in 3-aminopentane. There's 3-aminopentane. There's no carbon with 4 different groups bonded to it, and therefore there's no chiral centers. There's no chiral carbon or no asymmetric carbon atom.